Hello and welcome. Luke Skywalker and Obi-Wan Kenobi are sitting in a Chinese restaurant, and Luke's having a little trouble with the chopsticks. Finally, Obi-Wan leans forward and says, "Use the forks, Luke." In this exciting climax of our trilogy, we're going to look at graphing using calculus. I'm excited to get started. Let's get to it. So here we're going to bring together all of the knowledge that we've learned about how to find the domain of a function, how to find x and y intercepts, how to find horizontal and vertical asymptotes, how to find the first and the second derivatives, and where they're zero and do not exist, how to do a sign analysis on those first and second derivatives, and how to put all of this together to find local maxes, local mins, inflection points, and then graph the function. So those are going to be our 7 steps as laid out here. Let's get right into it with example 1. So our first we're asked to sketch the graph of f of x equals 3x to the 4th plus 4x cubed. Our first job is going to be to find the domain of the function. And here it's a polynomial, so nothing can really go wrong when plugging in x values. So our domain is going to be all real numbers, which we can write as negative infinity to infinity, or just write out all real numbers, or you can write the script r if you want to. Any way you like to write the domain is fine. Next, we're going to look at the x-intercepts. Here, to find the x-intercepts, you'll set y equal to 0, or in other words, your function equal to 0. In this case, our function is 3x to the 4th plus 4x cubed. So when we set that equal to 0, we'll factor out the x cubed, and then set each of those factors equal to 0. And we get x equals 0 and x equals negative 4/3. And I'm going to write those as points. So 0, 0, and negative 4/3, 0. They both have y coordinates of 0 because that's what we did at the beginning. We set y to equal 0 to find these x values. Those are x-intercepts. Now to find the y-intercept, if there is one, you set x equal to 0. So you plug in 0 into the function, and here we just get 0. And that's not too surprising because if 0, 0 was an x-intercept, then 0, 0 has to be a y-intercept as well. 0, 0, the origin, is the only place that's both an x and a y-intercept. Next, we're going to look at if there are any vertical or horizontal asymptotes. For vertical asymptotes, we look at this polynomial and we think, there aren't any vertical asymptotes. Polynomials don't have vertical or horizontal asymptotes for that matter. There aren't any places where they're undefined, and just generally speaking, no vertical asymptotes for polynomials. And no horizontal asymptotes for polynomials either. So I'll just say none, since f is a polynomial. Now the fourth step we're going to take is find the derivative of f. And we get 12x to the 3rd plus 12x squared. Here we'll factor out the common 12x and we get x plus 1. Then we'll figure out where this first derivative is equal to 0 and where it doesn't exist. I'm going to write f prime equal to 0, just for shorthand. And we've got the nice factored version of f prime. And we get 2 places, x equals 0 and x equals negative 1, where the first derivative is equal to 0. 2 solutions to that equation. Then we'll check to see if there are any places where the first derivative does not exist. And there aren't really any places where that happens because this is a polynomial for the first derivative and it exists everywhere. So first derivative exists everywhere. It's defined everywhere. Now let's look at the second derivative. Here I'm going to take the second derivative from the 12x cubed plus 12x squared. So we get 36x squared plus 24x. Factoring out a common 12x, we get 3x plus 2 left over. And again, I'll figure out where that's equal to 0 and where that does not exist, if anywhere. It's equal to 0 when it's equal to 0, which is x equals 0 and x, writing a little too fast, and x equals negative 2/3. And does not exist, well, there aren't any x values where the second derivative does not exist. Again, it's a polynomial. Now what we're going to do in the fifth step is our sign analysis. We're going to take all of the x values where either the first derivative or the second derivative was 0 or DNE and throw them all together on a number line. So there were three x values. There was x equals 0, x equals -1, and x equals negative 2/3. X equals 0 was duplicated, but we're just going to look at it once. So we're going to write -1, negative 2/3, and 0. You just have to write them in order. Don't have to necessarily draw them to scale. Then we're going to make a row for the first derivative and a separate row for the second derivative. So we're combining the first derivative and the second derivative together in this sign analysis. Now we said that the first derivative was equal to 0 at x equals 0 and x equals -1. So that's here and here. And there wasn't any place where the first derivative was DNE. Now the second derivative was 0 at x equals 0 and x equals negative 2/3. And was DNE nowhere. So these are just markers for where the first and second derivative might be changing signs. They might change signs as they cross 0 or DNE. Now we're going to go ahead and do a sign analysis for the first derivative by plugging in an x value in that first interval, say -2, for example. If we plug in -2 into the first derivative, we're going to get, well, the 12 is positive, the -2 squared is going to be positive, and -2 plus 1, that's negative. So we're going to get a negative overall. Now, as we cross -1, the corresponding factor x plus 1 is going to flip signs, and that has an odd multiplicity, so that sign flip will pass on to the whole function, to the whole first derivative. So as we cross -1, because we have an odd exponent for x plus 1, the whole sign flips to positive. And that's going to stay positive at -2/3 and between -2/3 and 0, because the only x values where the first derivative might flip signs are -1 and 0. Those are the only places where it could flip signs, because those are the only x values where the first derivative was 0 or DNE. So all along the interval from -1 to 0, the first derivative is positive. Then after 0, as we cross x equals 0, the corresponding factor x has an even multiplicity, so there isn't going to be a sign flip. That square will eat the sign flip that would have happened, and so there's no sign flip overall for the first derivative. Okay, so there's the first derivative. To get the second derivative, we'll take some x value that's less than -2/3. We could use like -1, for example. We'll plug it into the second derivative. So we'll have, let's see, the positive 12, and then negative value for x, and then -3 plus 2, that'll be negative as well. So overall, we get a positive value for the second derivative. And that positive will expand until it bumps up into a 0 or possibly a DNE. So it'll be, second derivative will be positive on the interval from -∞ to -1, and then from -1 to -2/3 as well. It's not going to change until we bump up into a 0 or a DNE. So now we bumped up to a 0, so that's at -2/3. As we cross -2/3, the corresponding factor is 3x plus 2, which has an odd multiplicity, so an odd exponent, and so we're going to flip signs. That'll flip from a positive to a negative. Then as we cross 0, the corresponding factor is x, which has an odd exponent, so we're going to flip signs. Let me clean that up. Okay, now we have the signs for the first and the second derivative. Before we get into the sixth step of finding local maxes and local mins and inflection points, let's go ahead and figure out what this is telling us, the sign analysis that we just did. What is that telling us? Well, first off, what is this negative telling us for the first derivative? If you said that it's telling us the graph is decreasing, or the function is decreasing, that's correct. Negative first derivative means that the function is going down as you go to the right. What about the second derivative, positive? What does that say? If you said concave up, then that's correct. So not only is the graph decreasing, going down as you go to the right, but the graph is concave up, so it's part of a cup. If we think of a cup, then the downward part of the cup, the decreasing part of the cup, is this left side of the cup. So connecting these two dots, we can draw something that bends in a concave up kind of manner. So this is just drawing a little snapshot of what the graph might look like, at least the behavior of the graph. Now on the next interval, we have that the first derivative is positive, which means what? If you said increasing, that's correct. And the second derivative is positive, and what does that mean? If you said concave up, that's correct. So increasing and concave up. The increasing part means that as we move to the right, the dots are going up. And the concave up part means it's part of a cup. Now the part of the cup here that's increasing is the right half of the cup. So we're going to bend the curve in this way to match the shape of the cup. Okay, so what about the next interval? What is the behavior both from what the first derivative and the second derivative tells us? So if you said increasing and concave down, that would be correct. Concave down, let's look at what concave down looks like. Concave down would be like a frown. Now if we're increasing along that frown, we're going from here to here. So we're on this part, this left side of the frown. So if we're going to be increasing and concave down part of a frown, it looks something like that. Now the last interval is, what is this? Increasing and concave up, looks like. So increasing and concave up, so part of a cup. We actually looked at that on our second interval. Second interval was also increasing and concave up. So now we have a sense of what the graph looks like. Now, it's not going to just be in little pieces like this. We're going to have to somehow connect these pieces together. But this is what the behavior of the graph looks like on each of the intervals. This is going to help us visually when we have to find the local maxes and local mins. When you draw the graph, you can see the local min happening at -1. So there's going to be a local min here at -1. The y value you can get by plugging in -1 into the original function. You'll get -1, it turns out, for the y value. So this we get by plugging in -1 into the function. And so that's our min. Now, that's the only, and if we think about the first derivative test, we can think, oh, okay, this makes sense because the first derivative is changing from negative, which is going down, to positive, going up, so decreasing to increasing. So there's definitely going to be a local min at that x value of -1. Notice that you can also read this sign analysis chart the way we've written it up using the second derivative test. X equals -1 is a place where the first derivative is equal to 0, which you need for the second derivative test. And then if you look at what happens when you plug that -1 into the second derivative, you get a positive value. So that means that the graph is concave up going through that point, which means there's a minimum right there at the bottom. So the second derivative test we can look at by just looking at what's happening at -1. First derivative test would be looking at the sign of the first derivative as we cross -1. But in either case, we get that there's a minimum at x equals -1. Now there aren't any other sign flips for the first derivative, so there aren't any other maxes or mins. So let's look for inflection points. Remember, inflection points are second derivative. We have to look at the second derivative and see if the second derivative changes signs. Because when the second derivative changes signs, that's a change in concavity, which means we're going to potentially have an inflection point there. So it looks like there's a sign change for the second derivative. As we cross negative 2/3, it goes from positive to negative. So we're going to have an inflection point there. Negative 2/3, comma, whatever f of negative 2/3 is, and I think it turns out to be negative 16 over 27. So you go back to the original function to plug negative 2/3 in. Just to drive home the point, so it's back to this original function right here. So we're plugging -1 or negative 2/3 into the original function to get the y value of the point on the graph. So then there's also a change in concavity as we cross x equals 0. So we have another inflection point, 0, comma, and then the y value there is 0. So again, you get the y value by plugging in 0 into the original function. Now, if you thought there was going to be a minimum somewhere and you plugged in the x value and you got undefined for the original function, that just means that there's not a minimum there after all. There just isn't a point on the graph there. Same thing with inflection point. If you think there's an inflection point because the concavity is changing, but you go to plug that x value in and you find out, oh, the function's undefined, well, then there's not a point on the graph there, so there can't be an inflection point. So then you just erase the fact that you just did an inflection point and hope nobody's looking. Okay, so we're going to put all of the information that we collected together, throw it on the graph, and see what we've got. Now we found an x-intercept, we found two x-intercepts, 0, 0, and negative 4/3, comma 0, and a y-intercept of 0, 0. So we'll put those in there. Here's 0, 0, negative 4/3, comma 0 is about negative 1 and 1/3, comma 0. We found a minimum of negative 1, comma negative 1. That's right here. We found an inflection point of negative 2/3, comma negative 16 over 27. That's going to be right around here, let's say. And then another inflection point at 0, 0. Well, we already have a point in the graph there. Now we're going to piece together all of the little bits of the graph that we're looking at. So on this first interval from negative infinity to negative 1, the graph is decreasing and concave up. So from negative infinity to this point at negative 1, so we're going to have to cross through this point and get down to this point, which is our local min. The graph is going to be decreasing and concave up, like part of a cup. So it's going to be fairly steep. Try one more time. It's going to be fairly steep. We're going to try to draw that concave up behavior as we're coming into that point. Now I'm going to draw this arrow here to say that the graph continues on in that direction because the domain is all real numbers, so there is more graph to the left. But we just want to make the graph look as much as possible decreasing, and that's not hard because it's very steep, and then concave up, so part of a cup, very steep cup. Now in the next interval from negative 1 to negative 2/3, that's from this point here to this point here, the graph is increasing and concave up. So we're going to draw a little curve that's increasing and concave up to connect those 2 points. Then from negative 2/3 to 0, in other words, from this point to this point, we're going to draw a graph that's increasing and concave down. So now it's going to bend concave down. Then from 0 to infinity, the graph is going to be increasing and concave up. So it'll look something like this. And there's a great sketch of our function using calculus. In the next video, we're going to look at introducing vertical and horizontal asymptotes, reviewing how we get them, and then using those to graph a rational function. Thanks for watching, and see you in the next video.